Hello, here is tutorial 3 question 2. So here we are given a displacement time graph of a spring mounted body having a mass of 4000 kg. It is released from a displaced position with 0 velocity at t equals to 0 second. So let's just highlight the key words here. We are asked to find the actual and the undamped natural frequencies. So this actual will be omega d. Undamped natural frequencies, we will have omega n. The spring stiffness, which will be k. And the critical and actual damping coefficients, which will be CO and C. Okay? So let us now write what we are given and what we are supposed to solve for. We have a mass of 4000 kilograms. We are also given an initial condition where it is 0 velocity at time equals to 0. And how do we represent that? So for velocity is x dot, right? What goes into the bracket is the time, which is 0 second, and the velocity is 0. There is also another initial condition which we can find from the graph, right? So when time is equals to 0, its displacement is 40 mm, right? So again, we can represent this with displacement, which is x. At time equals to 0, we have 40 mm. Okay, we are asked to find the actual natural frequency, which we put with a subscript d for damped natural frequency. Omega n, which is the natural frequency of the system. The spring stiffness, the critical damping coefficient, and the damping coefficient C. So what system is this? If we observe from the graph, we can see the amplitude is diminishing over time, right? So this is a subcritical damping. We can also call it underdamped. And for such system, the damping ratio will be less than 1. Zeta damping ratio will be less than 1. So for an underdamped system, we have a general equation where the amplitude x will be equals to E minus zeta omega nt P cosine omega dt plus Q sine omega dt, right? So we have a P and a Q, which is what we want to solve, and we are going to use the initial conditions to help us derive P and Q so that the equation is specific for this system, right? So let's first use the first initial condition. Where x0 is equals to 40 mm, right? If we were to substitute this into equation 1, right? Amplitude x is equals to 40 equals to e to the power of 0, because t is 0, 0 multiplied by this whole term will be equals to 0, we have p cos 0 plus q sine 0. Right, you can see that this makes solving it very straightforward because of the 0, and sine 0 will be equals to 0, cos 0 is equals to 1, and therefore we have solved for p is equals to 40. So likewise, we will use the second initial condition of the velocity at time 0 equals to 0 to solve for q. So our second initial condition is velocity is equals to 0 when time is equals to 0. So because we have a velocity term here, we'll differentiate equation 1 with respect to time to get velocity. So x dot will be equals to minus zeta omega n e minus zeta omega n t, right, p cosine omega dt plus q sine omega dt plus omega d e minus zeta omega nt minus p sine omega dt plus q cos omega dt. Right, so this is product rule. Right, we hold the first term, we differentiate the second term, plus holding the second term, differentiate the first term. So now that we have x dot, we can substitute the initial condition over here. Right, so x dot is equals to 0, velocity is 0, is equals to, and now we substitute all the t's with 0, minus zeta omega n e to the power of 0. Right, we have derived our p, we can insert it here, 40 cosine 0 plus q sine 0 plus omega d e to the power of 0 minus p, again 40 is substituted, sine 0 plus q cos 0. Right, again sine 0 is 0 and cos 0 is 1. Okay, so e to the power of 0 will be equals to 1, and that will give us this equation, minus zeta omega n 40 plus omega dq. Let's call this equation 3. Right, so let's rearrange the term. Q is equals to 40 zeta omega n over omega d, and 40, let's substitute omega d with, right, omega d is equals to omega n square root 1 minus zeta square, right, and this will be equals to 40 zeta over 1 minus zeta square. Okay, so we have our Q. Now let's solve for all the unknowns that we are asked to. The first is the actual natural frequency, omega d. So what we can notice is from the graph here, right, one period is, right, this is going to be one period, and it is 3 seconds. So from the sketch, we know 1 period is equals to 3 seconds. Therefore, we are able to find our actual natural frequency, or you can call it the damped natural frequency, right, which is omega d, and this is equals to 2 pi over t, right, where t is the period. So if we substitute 2 pi over 3, we'll get 2.094 radian per second. Okay, so the first unknown, omega d, is solved. Next, let's substitute our P and Q, which we have derived, into equation 1. Right? And we get this equation, which is specific to our system. So that's our P, which is 40 cosine omega dt, plus our Q, which we have derived, 40 zeta over root 1 minus zeta square sine omega dt. Let's call this equation 4. Okay, so when time is equals to 1, x is equals to 0, right, from the graph. Right, when time is equals to 1, we have x is equals to 0. Therefore, from equation 4, right, for x to be equals to 0, right, either our E term is equals to 0, or whatever is in the bracket must be equals to 0, right? So either this term here is equals to 0, or whatever is in the bracket is equals to 0. 0 times something is equals to 0. But if we observe, since for t is equals to 1, our E term minus zeta omega n 1 cannot be equals to 0, right? Therefore, we need our terms in our bracket to be equals to 0. So since we need our terms in our bracket to be equals to 0, let's write the terms here. We have 40 cosine omega dt. So we have derived omega d as 2.094 times t, which is 1 second, plus 40 zeta over 1 minus zeta square sine 2.094 times 1. So this whole term is going to be equals to 0. And we're going to solve for zeta now. So if we were to divide by 40, we will get cosine 2.094 times 1 and bring the next term to the right hand side, is equals to minus zeta over 1 minus zeta square sine 2.094 times 1. Right, notice that here we have used 40 as a 40, which is in mm. Right, you may ask how come we didn't convert it to meters. So it will be still the same, because if we convert it to meter, it will be 0.04, and this term is also 0.04, and they'll cancel out and you still get the same answer. Okay, let us continue. So we have a cosine on the left and the sine on the left. We can simplify it with a tangent, right? Because I'll just write it here. Tangent x is equals to sine x over cos x. Okay, so tangent 2.094, we will get minus 1.734. Right, so rearranging them, zeta square equals to 1, and therefore we can solve for our zeta, which is our damping ratio. Zeta will be equals to 0.499, which is approximately 0.5. So we have derived omega d, we have zeta, and now we can proceed to find all the other unknowns that we are asked to solve. So first, the natural frequency, right? Omega n is equals to omega d over 1 minus zeta square. So just direct substitution of omega d and zeta. We will get 2.418. So this is the natural frequency of the system. So when we get omega n, we can get the spring stiffness, right? Because omega n is equals to K over M, spring stiffness over mass. Therefore, the spring stiffness K is equals to omega n square multiplied by the mass, which is 4,000 kilograms. This will give us 23386 Newton per meter. Okay, so we are also asked to find the critical and the damping coefficient, which we will do so with the help of our damping ratio, which is our zeta, and it is equals to C over 2m omega n, right? Therefore, our damping coefficient C is equals to 0.5 times 2 times 4,000 times omega n 2.418, which is equals to 9672. And finally, the critical damping coefficient, right? So what's the relationship with zeta? Is C over CO. Right, so CO is equals to 9672 divided by damping ratio 0.5, and that gives us 19344. Okay, so we have solved for all the unknowns, right? That's it for tutorial 3 question 2.